We're in section 5.3, and this is example 2, part D. So we have the integral from 0 to 2, the absolute value of 2x minus 1. So we don't have an elementary and antiderivative for the absolute value function, and then also you got the 2x minus 1 in there. So a couple things going on here where we don't know how to do this off the bat in the way that we've been doing so far. If you look at the problem in part C above, we did have an elementary antiderivative for sine x. It was negative cosine x. So we could just go ahead and use fundamental theorem of calculus part 2 and go ahead and evaluate that integral. So just like when we were trying to take derivatives of the absolute value of some function, we're going to do the same strategy here, in that we can think of this function absolute value of 2x minus 1 without the absolute values as a piecewise function. So the way we break it up is if you have 2x minus 1, that answer being negative, then a different way of determining the absolute value is just to take the negative of that. If you already get a positive answer for 2x minus 1, then it just remains positive. So if you break this up into two pieces, where the positive piece occurs for x, that when you solve this function 2x minus 1 being greater than 0, that will give you the x for which we have 2x minus 1 being positive. And that'll give us the border also for the other piece. So just doing this as side work, what we're going to get is x has to be greater than 1/2. So somewhere you need to put the 0 case, and it really doesn't matter which one. I'm just going to go ahead and put it with the positive case, and that will suffice. So here's the directions that follow. It's 2x minus 1 if x is greater or equal to 1/2. So the other piece will be if x is less than 1/2, we get a negative value for which we throw another negative out front, and that'll make a negative times a negative, which is positive. So this is a way of getting around the absolute value function without using the absolute value symbols. So now let's look at our interval for the integrals from 0 to 2, and note that our pieces are divided up here at 1/2. And so 1/2 is on the interval from 0 to 2. So we're going to use this property that we've been sort of using a little bit when we were doing graphical approach to the definite integral. But we're going to use it here for piecewise functions, and I'll draw a picture at the end illustrating this. But property 5 was the one that said if you have an integral on the interval a to c, you can break it up into two pieces. Actually, let me get my notation right, it was a to b. But that's equal to the integral from a to c, where c is between a and b, plus the integral from c to b. So this is where c is in between a and b. So that's the property, and now we can go ahead and do two integrals using this property 5 to take the integral of 2x minus 1, the absolute value of that, from 0 to 2. So I break it up where the function is defined with these different pieces. So the first interval is going to be from 0 to 1/2, because that's characterized by the function, and I can distribute the negative of negative 2x plus 1. And then what this property says is I can add the other piece, starting at 1/2, to the end of the interval 2 with the other piece, 2x minus 1. So we do two separate integrals that they're going to be very similar, but now it's really easy. I can just take the integral, or think about taking the antiderivative of each term separately. So negative 2x, what I'm going to get there is negative 2 over 2x squared, plus the antiderivative 1 is just x. And then I'm going to evaluate that from 0 to 1/2. Plus, I get a really similar antiderivative here, just changes in sign. 2 over 2 x squared minus x, and that's from 1/2 to 2. So now plugging in, using the fundamental theorem of calculus part 2, I'm going to first evaluate this function with the 2's canceled out. You have negative of 1/2 squared, and then plus 1/2 minus, what's going to end up being a 0 here. I'm just going to note that instead of writing in all the details there. And then I'm going to evaluate the second function at 2. So it's 2 squared minus 2. And then minus, being careful here with some grouping symbols because I have multiple terms here. And I will have 1/2 squared minus 1/2. So going ahead and doing this, I'm going to get negative 1/4 plus 1/2 plus, let's see, 4 minus 2 is 2, and then I'm going to get minus 1/4 plus 1/2. So keeping going here, putting all those together, I should get 5/2. So that's the result. I'm just going to give you a quick picture here of what's going on. Both these pieces are linear functions, and the character changes at x equals 1/2. And the interval is from 1 to 2, or excuse me, 0 to 2. And so if we graph this first part, we have a negative slope, and then our second piece looks like this. And so what this property is doing, this first section right here is the integral from 0 to 1/2 of negative 2x plus 1. And this piece here is the integral from 1/2 to 2 of 2x minus 1.